In second part of flow in circular pipes, today we are starting with heat transfer correlations. For heat transfer in circular pipes, various correlations have been suggested depending on the flow conditions, that is laminar or turbulent. For laminar flow, heat transfer in circular tube with constant wall temperature is given as Cedar and Tate by 1936, proposed as the following correlation. Nu, that is Nusselt number, equals to 1.86 into Reynolds number into Prandtl number into D by L ratio to the whole power 1 by 3 into mu by mu W to the whole power 0.4. Here, all the properties except mu W are evaluated at mean bulk temperature. This equation is valid for Reynolds number Re in the range of 13 to 2030, PR, that is Prandtl number, between the range of 0.48 to 16,700, and mu by mu W in the range of 0.0044 to 9.75. Here, bulk and concentration temperature for flow inside pipes at a particular location in pipe is the average temperature for concentration if the fluid were thoroughly mixed. Sometimes it is called as mixing cup temperature for concentration. The bulk temperature and bulk concentration are denoted by TB and CB respectively and are defined by TB equals to double integration of Vz into T into dA upon double integration of Vz upon dA. And similarly, the bulk concentration is given by double integration of Vz into C into dA upon double integration of Vz into dA. Here, Vz is the component velocity in the direction of mean flow, that is, the velocity of the flow. For the case of flow past bodies immersed in an infinite fluid, the bulk temperature and bulk concentration become the free stream temperature and free stream concentration respectively, that is, TB equals to T infinity and CB equals to C infinity. Film temperature and concentration. The film temperature TF and film concentration CF is the average of the bulk surfaces, that is, TF is given by TB plus TW. TB is the temperature of the bulk and TW is the temperature of volume, the mean average. So TB plus TW by 2. Similarly, CF is concentration of bulk CB plus concentration at wall, that is CW, by 2. For turbulent flow, the following correlation approximates the physical situation quite well for the cases of constant wall temperature and constant wall heat fluxes. Some of these correlations are Dittus and Boulter in 1930. It is proposed as the following correlation in which all physical properties are evaluated at mean bulk temperature. It is given by Nu, that is Nusselt number, equals to 0.023 into Re, that is Reynolds number, to the power 4 by 5 into Prandtl number to the power n. Here Re is the Reynolds number of the particle and Pr is the Prandtl number, and n changes from 0.4 to 0.3. Here 0.3 for cooling and 0.4 for heating. The Dittus-Boulter correlation is valid only when Prandtl number is between 0.7 to 160 and Reynolds number is greater than 10,000. Also, the L by D ratio should be greater or equals to 10. Second correlation, Cedar and Tate in 1936. The correlation is as follows. Nusselt number equals to 0.027 into Reynolds number of the particle, that is Red, to the whole power 4 by 5. Prandtl number to the whole power 1 by 3 into mu by mu W to the whole power 0.14. In which all properties except mu W are evaluated at mean bulk temperature. Similarly, this equation has some restrictions of Prandtl number should be between 0.7 to 16,700. Reynolds number should be greater or equals to 10,000 and L by D ratio should be greater or equals to 10. Third relation, Whittaker correlation. Here, the Nusselt number equals to 0.015 into Reynolds number of the particle to the whole power 0.83 into Prandtl number to the whole power 0.42 into mu by mu w to the whole power 0.14, in which the Prandtl number dependence is based on the work of Feikind and Metzner in 1958, and the functional dependence of mu by mu w is the work from Cedar and Tate in 1936. All physical properties except mu w are evaluated at Meehl-Burke temperature. The Whittaker correlation is valid for the given ranges. Reynolds number should be between 2300 to 10 to the power 5. Prandtl number should be between 0.48 to 592, and mu by mu w should be between 0.4 to 2.5. Now, calculation of heat transfer rate. Once the average heat transfer coefficient is calculated, once the average heat transfer coefficient is calculated from correlation by using equations, then the rate of energy transferred can be calculated using Q equals to pi dl. This is the cross section area of the circular pipe. H is the heat transfer coefficient. D is the diameter, and T Lm. dLm is the logarithmic mean temperature difference between the both wall temperature and bulk temperature, and it is given by delta TLm is given by Tw minus Tb of inside minus Tw minus Tb of outside whole upon log of Tw minus Tb of in upon Tw minus Tb of out. Now let us look into an example for heat transfer correlations. It is example 4.16 of modeling in transport phenomena. The question is, air at 20 degrees Celsius enters a circular pipe of 1.5 centimeter internal diameter with a velocity of 50 meter per second. Steam condenses on the outside of the pipe so as to keep the surface temperature of the pipe at 150 degrees Celsius. Now we have to calculate the length of the pipe required to increase air temperature to 90 degrees Celsius, and discussing the effect of surface roughness on the length of the pipe. So all the physical properties given to us are the mean bulk temperature, that is the average of 90 and 20 degrees Celsius, that is 55 degrees Celsius. For air we have density at 20 degrees Celsius. At 55 degree we have viscosity, kinematic viscosity and Prandtl number. For air at 150 degree we have viscosity. Now initial analysis. The inventory rate equation for mass reduced would be the rate of mass of air in would be rate of mass of air out. That would be equals to our mass flow rate. Now we know mass flow rate can be written as pi d square by 4. This is the area into rho into V of inlet. So we get the mass flow rate as 1.06 into 10 to the power minus 2 kg per second. In the problem with the flow of compressible fluids, we have to define a component, that is mass velocity, denoted as G. G can be written as G equals to mass flow rate by area or rho into V. The advantage of using G is the fact that it remains constant for steady flow of compressible fluids through ducts of uniform cross sections. So we calculate G as 60.24 kg per meter square per second. Now let us do the energy balance. Rate of mass in should be rate of mass out. Rate of mass in would be mass flow rate into Cp into delta T, that is Tb in minus T Ref plus pi dl. This is the cross section. H is the heat transfer coefficient, and delta TLm is the logarithmic mean difference of the temperature. Similarly, the rate of energy out would be simply mass flow rate into Cp into delta T. Here delta TLm is the logarithmic mean difference of the temperature. Using equations 1, 3, 4 and 5, we get L by D ratio equals to 1 by 4 V by rho Cp by H into log of Tw minus Tb in upon Tw minus Tb out. This could be written as in the form of value of Stanton number or also Nusselt, Reynolds and Prandtl number. So we get the final equation of L by D equals to 1 by 4 of Stanton number log of Tw minus Tb in upon Tw minus Tb out. Or we could also write it as 1 by 4 of Reynolds number into Prandtl number upon Nusselt number into log of Tw minus Tb in upon Tw minus Tb out. We will use this equation further. Now we would also like to calculate the Reynolds number, which is given as D into G by mu. Here Reynolds number comes as 45,636 and this is clearly a turbulent flow. So we will use the three relations we studied earlier. Firstly, Dittus-Boelter correlation. Here we replace the Nusselt number in the L by D equation. So we get the Nusselt number. So we calculate the L by D ratio, which comes as 58.3. Now we know the value of D, so we calculate the value of L, which comes as 87 centimeter. Similarly, in Cedar-Tate correlation, we substitute the value of Nusselt number and get the value of L by D ratio as 49.9. We know the value of D as 1.5, so we get the value of L as 75 centimeter. Similarly, in Whittaker correlation, we insert the value of Nusselt number in the L by D equation and get the L by D ratio as 67, and similarly the L value as 101 centimeter. This is our A part done. For B part, we need to have various values of epsilon by D and calculate the values of F, L by D and L. This can be easily done by using Stanton number. This was the equation derived earlier. Now we know that Chilton-Colburn analogy gives us F by 2 equals to Stanton number into Prandtl number by to the power 2 by 3 for heat transfer. Substituting this value, we get a correlation of L by D. We get a correlation of L by D in terms of friction factor. Now earlier we used these two equations for turbulent flow in momentum transfer. Similarly, we can use this in heat transfer too. We have value of F from Reynolds number and epsilon by D and also by L by D ratio. So we simulate all the values and get this table. This is the various values of epsilon by D, F, L by D and L at given instances. Next we have mass transfer correlations. In mass transfer correlation, we have the cylindrical tubes is encountered in various operations such as wetted wall columns, reverse osmosis and cross flow ultrafiltration. As in the case of heat transfer, mass transfer correlation depends on whether the flow is laminar or turbulent. Let us start with the laminar flow. Here we have an equation of Sherwood number as 1.86 into Reynolds number into Schmidt number into D by L ratio to the whole power 1 by 3. The above equation is valid for Reynolds number to be in the range of 2000 to 35,000 and Schmidt number to be in the range of 0.6 to 2.5. Next we have for turbulent flow correlations. This correlation was proposed by Linton and Sherwood in 1950 and this relation is Sherwood number equals to 0.023 into Reynolds number to the power 0.83 into Schmidt number to the power 1 by 3. The above equation is valid for Reynolds number to be in the range of 2000 to 35,000 and also Schmidt number to be in the range of 0.6 to 2.5. Once the average mass transfer coefficient is calculated from correlations given by the above equation, the rate of mass transfer of species A transferred is calculated as MA equals to pi dl. This is cross section area into Kc. This is mass transfer coefficient, comma delta Ca into Lm. This is logarithmic mean difference of concentration into Ma. Here Ma is the molecular weight of species A and delta Ca Lm. This denotes logarithmic mean value of the concentration, which is given as CaW, that is concentration of A at wall, minus Cab, that is concentration of A in bulk, in, minus Ca wall minus Ca bulk out upon logarithmic value of Caw minus Cab in upon Caw minus Cab out. Now let us see a question on mass transfer correlations. It is example 4.17 of modeling in transport phenomena. It says a smooth tube with an internal diameter of 2.5 cm is cast from a solid naphthalene. Pure air enters at a tube at an average velocity of 9 meters per second. If the average air pressure is 1 atm and the temperature is 40 degrees Celsius, estimate the tube length required for the average concentration of naphthalene vapor in the air to reach 25% of the saturation value. Firstly, we calculate the diffusion coefficient of naphthalene, that is A, in air B at 40 degrees Celsius using the diffusion coefficient at 300 Kelvin, which is 0.62 into 10 to the power minus 5. So we get DAB at 313 Kelvin or 40 degrees Celsius as 6.61 into 10 to the power minus 6 meters square per second. For air at 40 degrees, kinematic viscosity is given as 16.95 into 10 to the power minus 6 meters square per second. So we can calculate the Skimmett number as kinematic viscosity upon DAB, which comes out to be 2.56. Now, initial assumptions we have are steady state conditions prevail and the system is isothermal. Initially, we balance out the moles of A. The rate of moles A in would be the rate of moles of A out. The rate of moles of A can be given as pi dl. This is cross section area. Kc is mass transfer coefficient. And delta CaLm is the logarithmic mean value of concentration. Similarly, the rate of moles of A out would be QCAB out. Here Q is the volumetric mass transfer, volumetric rate, and CAB out is the concentration. This would be given as pi d square by 4 into velocity into CAB out. Here delta CaLm would be given as CAB out upon logarithmic of CaW upon CaW minus CAB out. As we done in the heat transfer correlation, we derive the L by D equation, which comes out to be L by D equals to 0.072 1 by Stanton number for mass transfer equals to 0.072 into Reynolds number into Skimmett number by Sherwood number. The value of L depends upon the correlations. Now, using Chilton-Colburn analogy, we get L by D equals to 0.072 into 2 by F of Skimmett number to the power 2 by 3. Calculating Reynolds number for this problem, we have Reynolds number equals to D into velocity by kinematic viscosity, which comes out to be 13,274, which is in turbulent flow. Now calculating friction factor using Chen correlation, which we used in the momentum transfer for turbulent flow. We calculate the value of A, which comes out to be 1.16 into 10 to the power minus 3, and substitute this value in the friction factor equation. So the friction factor comes out to be 0.072. Hence the L by D equation becomes 0.072 into 2 into 2.56 to the power 2 by 3 by 0.0072, which comes out to be 37.4. This is the L by D ratio. Here D is 2.5 centimeters, so the length comes out to be 93.5 centimeter. Similarly, using Linton-Sherwood correlation, we get the L by D ratio as 3.13 into Reynolds number to the power 0.17 into Schmidt number to the power 2 by 3. We get the L by D ratio as 29.4 and L as the value of 73.57 centimeter. Lastly, we have flow in non-circular ducts. The correlation given for friction factor, heat transfer coefficients and mass transfer coefficient are only valid for ducts with a circular cross section. These correlation can be used for flow in non-circular ducts by introducing a concept of hydraulic equivalent diameter DH. Here DH is defined as 4 into flow area upon wetted parameter. The Reynolds number based on the hydraulic equivalent diameter is given as hydraulic equivalent Reynolds number equals to DH. This is hydraulic equivalent diameter into rho is density, V is the velocity, and mu is the viscosity of the fluid. So the friction factor based on hydraulic equivalent diameter is related to hydraulic equivalent Reynolds number in the form of F equals to ohm into R into 16 upon REH. Here REH is the hydraulic equivalent Reynolds number, where ohm depends on the geometry of the system. The hydraulic equivalent diameter for various geometries are shown below. First geometry are two pipes with a distance between B between them. The hydraulic equivalent diameter is 2B. For a rectangular plate of length A and breadth B, we have hydraulic equivalent diameter to be as 2AB upon A plus B. Third, we have an equilateral triangle with side A. Its hydraulic equivalent diameter is A by root 3. Lastly, we have a concentric circle with outer diameter of D0 and inner diameter of Di. Its hydraulic equivalent diameter is D out minus D in. Thank you.